Module 4, Pearson Coefficient of Correlation. Statistical methods of central tendency, variability, and locations help compare and analyze distributions involving only one variable distribution. However, describing the relationship between two or more variables is another essential part of statistics. In any educational research, the relationships between two or more variables are necessary. For example, to predict the behavior of learners using a learning management system, LMS, like Google Classroom, a teacher finds it relevant to know whether the availability of technology is related to its learning outcomes. The Pearson product moment correlation coefficient measures the strength of the linear relationship between two variables. It is referred to as Pearson's correlation, or simply the correlation coefficient. If the relationship between the variables is not linear, then the correlation coefficient does not adequately represent the strength of the relationship between the variables. The symbol for Pearson's correlation is P when it is measured in the population, and R when it is measured in a sample. Because we will be dealing almost exclusively with samples, we will use Pearson's correlation unless otherwise noted. As a statistical method, correlation helps know the relationship between two or more variables that may be related somehow. For example, the behavior of learners in the use of LMS and their readiness to adopt technology, height and weight, educational attainment and learning achievement, and so on. All these aspects involving two or more variables may be interesting if there is an association between the variables and whether this association is strong enough to be helpful. As a measure of the degree of relatedness of two variables, correlation is widely used in exploratory research when the objective is to locate variables that might be related in some way to the variable of interest. To compute the Pearson R, the formula is shown below. The formula is R equals N times the summation of xy minus the summation of x times the summation of y divided by the square root of N times the summation of x squared minus summation of x squared multiplied to N times the summation of y squared minus the summation of y squared. where x is equal to the observed data for the independent variable, y is the observed data for the dependent variable, n is the size of the sample, and r is the degree of relationship between x and y. Persons R can range from -1 to 1. An R of -1 indicates a perfect negative linear relationship between variables. An R of 0 indicates no linear relationship between variables, and an R for 1 indicates a perfect positive linear relationship between variables. Figure 1 shows a scatter plot for which R is equal to 1. To interpret the degree of relationship, the following values are used. On the first column, you have the size of correlation, while in the second column, you have the interpretation. 0.90 to 1 or -0.90 to -1 means very high positive or negative correlation. 0.70 to 0.90 or -0.70 to -0.90 means high positive or negative correlation. Positive or negative 0.50 to 0.70 means moderate positive or negative correlation. Positive or negative 0.30 to 0.50 means low positive or negative correlation. 0.00 to positive or negative 0.30 means negligible correlation. There are 3 correlation types. 1. Positive and negative. 2. Linear and non-linear. And 3. Simple, partial, and multiple. Positive and negative correlation. If both the variables move in the same direction, we say a positive correlation. That is, if one variable increases, the other variable also increases on an average. Or if one variable decreases, the other variable also decreases on an average. On the other hand, if the variables vary in the opposite direction, we say that it is a case of a negative correlation. Take a look at this figure. Figure 1. When R is equal to 1, this is a perfect positive linear relationship. Take a look at figure 2. When R is equal to -1, this is a perfect negative linear relationship. Now take a look at this figure 3. When R is equal to 0, this is a scatter plot showing that there is no relationship between X and Y. Linear and non-linear correlation. If another variable accompanies the change in one variable in a constant ratio, it is a case of linear correlation. On the other hand, if the amount of change in one variable does not follow a constant ratio with a change in another variable, it is a case of non-linear or curvilinear correlation. If a couple of figures in either series X or series Y are changed, it will give a non-linear correlation. Simple, partial, and multiple correlation. The distinction between these three types of correlation depends upon the number of variables involved in a study. If only two variables are involved in a study, the correlation is simple. When three or more variables are involved in a study, it is either partial or multiple correlations. In multiple correlations, three or more variables are studied simultaneously. However, in partial correlation, we consider that only two variables influence each other, while the effect of another variable or variables is held constant. In discovering the nature and degree of relationship between variables, the correlation analysis does not necessarily imply any cause and effect relationship between the variables. Two variables may be related to each other, but this does not mean that one variable causes the other. For example, we may find that the highest educational attainment and level of IQ are correlated, but that does not mean that the highest educational attainment could increase IQ. Always remember that causation implies correlation. However, the converse is not valid. The correlation coefficient is merely a mathematical relationship, and this has nothing to do with cause and effect relation. It only reveals covariation between two variables, even when there is no cause and effect relationship in bivariate series, and one interprets the relationship as causal. Such a correlation is called spurious or nonsense correlation. This will be misleading. As such, one has to be very careful in correlation exercises and look into other relevant factors before concluding a cause and effect relationship. Several formulas can be used to compute the person's correlation. Some formulas make more conceptual sense, whereas others are easier to compute. To begin with, we are going to begin with a formula that makes more conceptual sense. We will compute the correlation between the variables x and y shown in Table 1. We begin by computing the mean for x and subtracting this mean from all values of x. The new variable is called small x. The variable y is computed similarly. The variables x and y are deviation scores because each score is a deviation from the mean. Notice that the means of x and y are both 0. Next, we create a new column by multiplying x and y. Before proceeding with the calculations, let us consider why the sum of the xy column reveals the relationship between x and y. If there were no relationship between x and y, then positive values of x would be just as likely to be paired with negative values of y as with positive values. This would make negative values of xy as likely as positive values, and the sum would be negligible. On the other hand, consider that the high values of x are associated with high values of y, and low values of x are associated with low values of y. T is equal to r times the square root of n minus 2 divided by 1 minus r squared, with df equals n minus 2, where r is equal to the obtained person r value and n is equal to the sample size. Example 1. Assuming that an experimenter wanted to know of the ages of 15 employees have significant relationship with their performance appraisal. Table 1 shows its calculation of R. As you can see in the table in column 1, we have the 15 employees. In column 2, their corresponding ages labeled as X, with a total of 616 and a mean of 41 and 7/100. The third column is their performance, labeled as Y. The total is 923 with a mean of 61 and 53/100. The fourth column is the XY, followed by X squared, and the last column is Y squared. All these three columns have its corresponding total. Pearson's R is designed so that the correlation between age and performance appraisal is computed. To achieve this property, Pearson's correlation is being used. Using the formula of R, we will simply substitute the figures from the given table. Then, we are going to compute the R. In this particular case, R is equal to negative 0.03, which means negligible negative correlation. To determine whether the obtained R is significant, we compute the t-test for R. Using the formula, t is equal to negative 0.03. Then, get the square root of n minus 2, which is 13, divided by 1 minus negative 0.03 squared. Our t here is negative 0.108. The R result here is interpreted as follows. Pearson R is equal to negative 0 and 3/100. Strength is equal to negligible negative correlation. For the computed t value, which is negative 0 and 108 thousandths, the df is equal to 13.